a workshop with many seminars. And on Tuesday, there's going to be an outreach event in Rome. So we wanted to think of something different. We didn't want to just repeat what they were doing. So we decided to have some roundtable discussions here and involve all of Latin America. Obviously, it's supposed to be a global event, so it's not just Brazil. And it's also an opportunity for us. I think one thing that I think we want to do is have activities that involve all of Latin America. And of course, there's already a network in Brazil financed by FAPESP in São Paulo and CNPq for Brazil. But I think it might make sense to try to enlarge it to have some kind of network that we could, of course, help, but we're not going to organize, but we could help to create the network. And the idea is at least maybe to have a web page and mailing lists, and so people know what kind of activities are going on, especially for the students, so they can prepare and participate, and maybe it will seed collaborations. So hopefully in the afternoon, we can try to brainstorm about what would be the most useful way to do that. So we have a short video about ICTP-SAIFR, just to get some ideas of what other things we do here. And then we'll start the session for the morning. O som não está saindo. Okay, so one more thing I want to say is that there's not so many people in the audience, but that's good for you guys, because the idea is to make this participative. So the discussions are really supposed to be discussions. So there's short presentations, and then the idea is think about questions and really have a discussion. So, okay, so let's hope everything works out well.
Okay, so let's start this first roundtable on science, on quantum science. So the idea is that we will do 4 short presentations, 5 minutes. Let's try to stay within 5 minutes. And our first speaker is going to be Rodrigo Benevides, who is a joven pesquisador who recently started his group in USP. And he's going to talk about quantum transduction. Please.
Has a problem? Oh, now it's working? Yes, okay. So let's start over. So the idea is more like give you ingredients to make questions. Yes, it's fine. So yeah, as Dario said, I just started my group there at the University of São Paulo, ECOS. The idea of ECOS, well, stands for Engineered Quantum Control Systems. And our goal there will be, well, it's a group that really just started, right? I started early this year. And then the idea is to be, my expertise, my main expertise, I would say, that's working with microfabricated device, planning, then designing, then thinking about experiments and making it happen. But particularly interested in hybrid systems, systems that somehow interconnect two or more different platforms, right? So even though we just start, we have there a small group of people working with us. We're bravely working with our recently lab, because by lab, I just mean at the moment an empty renovating room that we hope that in a few months we'll have a lot of stuff. And we not just hope, but we are very happy that we are sure that this will happen, because we had recently got this grant from FAPESP that I imagine that probably Gustavo should mention in his roundtable, but together with this Quantum Technology Initiative from FAPESP. So we got a generous grant to start the lab, which will include, in our case, a dilution fridge will be basically the core of this lab, right? It's like this cryostat that we can bring samples up to a few millikelvin. And in our case, I will just explain in a few slides, but my goal will be to work with superconducting qubits, which also includes then in our grant the acquisition of this device to control them, and some optical setup. This will be ECOS, hopefully in, let's say, 1 year or so, we'll have this set up there, right? And our main goal at the moment will be to work with transducers. That's what was the title, right? Quantum transduction. And just to give us a hint of, an idea of what I mean, when we look at our daily life, we have a lot of classical transducers that we work in even without thinking about it, right? Like this microphone that I'm using, the loudspeakers in the room, or like some generators, CCD cameras, and keyboards. A lot of systems are working somehow, making some transductions, which are these elements that can transform energy from some type of, some physical form to another one, right? And then when we go to the quantum regime, we think that we also need to have such device, this type of device, where basically the general concept would have a system that can take a wave function, a given quantum state, and somehow make this transduction to another implementation, right? Of course, this toy model, this general idea here is very broad, and it will depend, the implementation on it will depend strongly on what kind of systems that we are trying to connect. But in our case, our main goal there at the moment is to connect two very important platforms for quantum information. On one side, the superconducting qubits, which are these devices that are the ones that are needed to be operated at very low temperatures. And they are very great to control and to work as, in fact, the quantum processing unit of this quantum information system. Because they give a lot of freedom of control of these states and are really flexible in the sense of what we can do there, but they are terrible in the transmission because of the necessity of working at these low temperatures. That is why we want to connect, and not just us. There's a big effort worldwide to try to connect this device with optical fibers because of the great communication properties that these fibers hold. So this is the idea of do what we call microwave to optical quantum transduction. And in our lab in particular, we are working with a specific implementation. We will try to make a specific implementation of that, which I call a modular quantum transduction, which is basically to use an intermediate device for that. in short terms, just because the directly connection of optics with superconducting circuits is very hard to be done. It's not really feasible. And then our idea will be to have this intermediate acoustic device, which the device itself that we are working on looks more like that, where we have different components here. That's why called modular, where we have then the superconducting qubit that electromechanically is coupled to a piezoelectric layer that creates these surface acoustic waves here. And then these will be inside an optical cavity, a Fabry-Perot cavity here, and optomechanical interaction will allow to read out this information. So we have here microwave, electromechanics, mechanics, optomechanics, and finally just optics. This is general concept of it, but of course we can discuss further on it. There's a lot of challenges involved onto that. I will not have time to go over all of them, but I will just highlight two that will be, I think, very relevant for the near future. One is the fabrication of this device. This is a big challenge in any field that involves microfabrication. Is always like how to make it happen, right? When we plan is much brighter and easier than when we need to do. And in our case, we are trying to work with the Polytechnic School at the University of São Paulo there, because they have an expertise on microfabrication, especially of microelectronic device. So we are working in very close contact with them, but now trying to bring this quantum aspect of the technology. And on the other one that I think will be a challenge for us is the technical challenge of constructing this environment. Even though most of this device is commercial, but we know that's a big difficulty because of the constraints that we need to operate these fridges. Okay, I hope I kept into the 5 minutes or so. So I just invite you to chat with us, and thank you for listening.
Okay, thank you very much. Let's go straight with the second speaker. Okay, here. Liliana, it's your turn. So I think it's a good idea that, you pass the necklace, and then we keep with the microphone. That is probably more efficient than... Yeah, you just, that is to allow the camera to follow you.
Okay, okay.
Yes.
Hi.
Okay, we need a few seconds more.
So, good morning.
Okay.
Okay.
I should
please
probably introduce you a little bit, right? So our next speaker is going to be Liliana Sanz de la Torre. She is a professor at Instituto de Física, Universidade Federal de Uberlândia, and she's now going to talk about a bird's eye view of the National Institute of Science and Technology of Quantum Information. Please.
Okay, thank you, Dario. Good morning. So this is not exactly science technology that I'm going to talk about. It's like a big break, but I will discuss a study we conducted some time ago and provide an overview of the National Institute of Science and Technology of Quantum Information. And I read because my English is really, really bad, so I don't want to spend, I don't know, 20 minutes because my English is weird. So our study were done in collaboration with Ruth Oliveira and Rafael Chavez from the IIP, International Institute of Physics, and it aims to understand the connection within the network of researchers participating of this National Institute, which is a big initiative of the government to promote science. The data is limited because we have to cut some time, and the data is from 2016 and April 2022. And includes only the research of the Institute, and of course there are more researchers in quantum technologies like Thiago and Gustavo, who at that time don't belong to the Institute. So the project director was Professor Belita Coiler at the Universidade Federal do Rio de Janeiro, and overseeing a team of 120 collaborating researchers. The Institute spans 20 universities, and the CBPF is the Centro Brasileiro de Pesquisas Físicas, across 12 states in 4 of the 5 Brazilian macro regions. So this is a map And you can see we are all over the place. And we analyze the academic contributions, which include 1,156 articles, with titles comprising 8,474 words. And with few exceptions, of course, the articles were written in English. And then quantum, of course, is the most frequently repeated word, and followed by entanglement. So we are in Brazil, at least in this community, we are interested in generation of entanglement as a resource. And other notable words include experimental, optical, and measurement. They stand out due to the significant work that in experimental physics, like in laboratories of Paulo Nussensweig, Professor Paulo Nussensweig, who I think was here. And of course, hey, how are you? And so we are particularly strong in quantum optics, atomic physics, and nuclear magnetic resonance. And now, very quickly, if we map the scientific production of ICTQ over the years, we observe that always surpass 150 articles, with the highest number published is 222 because we have to spend time at home, so we have time to do some work on some writing. Regarding the distribution of papers per journal, we know that PRA has the most published work, followed by PRL and PRB. And it is worthwhile to note that additionally there are 25 articles in high-impact journals besides PRL, including Nature, Science, Nature Communication, and Letters, and among others. Now, addressing the topic of collaboration, which is the main key of bringing this information here to you, oh my God. Okay. We observed that this, now, okay. We analyze the number of articles per co-authors per article, and we observed this peaking one. And this peaking one is because most of the institute researchers publish with their students and collaborators outside the project, the ICT. But we have the obvious thing, articles with n equal to 3, our co-authors are working in theoretical works, and articles with more than 3 co-authors as mostly experimental, with some exception, for example, this one, which is this article with the most collaborations done by 7 researchers from 3 institutions as co-authors. And this is a work with mixed theory and experiment. This is a map. This is the first of 3 graphics that I want to show. This is a map who I particularly loved a lot because, you know, this shows Brazil as a whole. And in colors, we highlight the regions where the INCT-IK researchers are. And the gray lines indicate the connections between researchers, and the size of the dots represents the number of researchers in each city. And it seems now, you can see that the community, the quantum information community, has extensive reach, not limited to capitals or a single macro region. We are all over the place. And then focusing in cities, we can better observe the connection within the network. The southeast of Brazil concentrates the majority of researchers and brings the majority of connection, but we have these major connectivity hubs, which is Rio de Janeiro and Niterói, so the state of Rio de Janeiro stands out in that scenario. And the gray lines are bolder when collaborations are more frequent. So this is really nice to a graph to see again when reading the paper. And then this is focusing in people. We observe extensive network connectivity with 85% of the researchers being part of this large cluster in the center. Our study identified 8 different communities, and this we have these big subjects in the words cloud in the paper. And we also discovered the most connected researcher in the network, who is Professor Antônio Selacechicuri from the Universidade Federal Fluminense. He is an experimental physics, and he's the top one. And then, last word, It was really fun. Finally, a word about human resources for the people who are not from Brazil. Until April 2004, when I checked the final time I have checked this, research at the INSTQ had mentored 425 PhD theses and 672 master dissertations, in addition to candidates for PhD and master, around 160, it's okay, it's there, and 120, respectively. And you know, these impressive numbers are the result of public investments, social CAPES and CNPq. They have scholarship programs here. You are not, for those who are from Colombia, we have to focus in research. We don't have to teach lessons and everything. It's a really, really big difference here from the other places. And of course, this community was built around these big projects, the Instituto de Milenio in 2000, and then the INCT, the continuation, the second life of Instituto de Milenio, which it starts in 2009. In ST 1.0, I like how to refer that. And 2014, which was this INCT. So more information, you can write to me, because we have the data and the code to analyze the data and generate the graphics. It's free, it's in the GitHub. So you can write, and I provide the link of the repository. And thank you very much for the opportunity to be here, and not to talk about physics, but about this political thing that maybe could enrich discussions in the second and in the third session. Thank you.
Thank you very much. Now we leave Brazil and we go to Argentina, because our third speaker is going to be Christian Schmiegelow. Yes, that is working. Christian Schmiegelow from Universidad de Buenos Aires and CONICET, and he's gonna talk about quantum optics at Universidad of Buenos Aires. Please.
So thank you very much for the invitation, and I'm really happy to be thinking about extending and formalizing and seeing ways of growing our quantum network in the whole of Latin America. I think it's something that has been happening, as we were talking yesterday evening with Nathan, with different degrees of formality and different kinds of tools that many people and our teachers and that will be a lot of them speaking later in the afternoon have been building over the years. But this is a wonderful opportunity. So I was asked to speak a little bit about my research in the lab in Buenos Aires. So the lab in Buenos Aires, we work mainly with ion trapping, ion and nanoparticle trapping, actually. What you see here is a picture of the first ion trap we built. It's a ring ion trap, and there in the center, if you see there's a little dots, that's 6 trapped ions in the center of the trap. This is not the condition in which we work normally. This picture was taken with help of a friend of mine who's an astrophotographer. So normally we work with a lens that actually just images the ions, not the whole setup with the ions in the middle. But I think it's a nice picture presenting the setup. So we, a little bit on the context of how this lab came to be. So after I did a postdoc stay outside of Argentina together with Juan Pablo and Miguel Rotonda, who were my PhD advisors. They supported me in getting grants, and actually reused some grants that had working in establishing the lab. And also together with Augusto Roncaglia, who was a theoretician with whom we still work there, we decided to start this lab in the University of Buenos Aires in a way that couldn't have been possible because of the normal funding ways that were there, which were not meant to, as we were told in the first talk, there were not big grants for starting labs. for young researchers, so we had to somehow bend the rules there with the help of Juan Pablo and Miguel and Augusto to get that done. And well, the lab is now nicely working. There's it has grown over the last, so we started in 2015 or 16, and now there are 6 PhD students. That's more or less the standard, that 4 or 5, 6 PhD students are, it's the maximum size that we can actually have in the lab. Associate researchers, and we're still working very much with our friends, theoretical collaborators around Buenos Aires. Just a little, before I continue to the next slide, a little thing. When I did my PhD student, I was also involved in starting a lab together with Miguel La Rotonda, and that lab was, so we never had any formal collaborations with a group of Luis and with Steve, who was there, and Paulon, but the building of that lab was possible due to the friendship and coming and going and learning and talking in between conferences and helping each other out with lab things and recommendations and things that wouldn't be possible without the Brazilian-Argentinian connection. Good. So our lab is, so this is a map of the world map of ion traps. In South America, currently we have 2 ion trapping groups. There's our group in Buenos Aires, and there's a group of Claudio Lenz, who's actually also doing ion trapping in the University of Rio. They're working with a slightly different technique and with another orientation, more into particle and fundamental high energy physics. Next, so what are these 2 slides are to tell you a little bit about what are our research interests and what are the things that we're doing in the lab. So there's 2 big projects. One of them is I put under the big name, or the big umbrella of quantum optics with ion traps. And there, so we have 2, so one I would say it's more like a tool and also a research direction, which is studying the interaction of atoms or single trapped ions or many ions with structured light beams. So we use beams that are structured spatially, and we see the way that this structure changes the way it interacts with atoms. We have a very nice work from last year where we demonstrated something which was actually very much connected to research that was done years before in Natal and also in Uruguay, which is we measured something called the rotational Doppler effect. And this somehow leads us a way of using these beams to observe something that is still not observed, but it's a very curious thing, which is called the super kicks, which is the chance that a photon kicks, impinges an ion in one direction and actually kicks it transversely. So like the momentum kick is not in the direction of where the wave is traveling. And we're studying ways of using these effects for temperature sensing and motional sensing, and also for using quantum gates with structured light. In this respect, we have also another trap, which is a linear trap, which allows us to trap linear ion crystals like this one's here. And in this trap, we're also going to be using these structured beams, for example, to sense temperature along ion chains like this one's, where we want to study. So we have different projects there where we are studying heat transport and thermodynamics of small ion chains. And we're also looking into generating and studying application of non-classical states, like squeeze states and non-Gaussian states in these traps. So that's for quantum optics with ion traps. There's this second big project that we work on, which is we call optical cooling of solids. There we're working with also a Paul trap, which allows us to levitate here. This is an image. You can actually see this with your eye, because this is a nanoparticle levitated also in a trap, this dot there. So the scattered light is much more than in the ion case, and you see a very bright dot there with your bare eye when you trap them, and we can trap one or many. And so there have been systems where people have demonstrated that you can do laser cooling, like in the standard Doppler cooling or Sisyphus cooling, or that until 10 years ago, this was only possible in gases. Now we know a couple of systems where this is possible in solids. One of the systems is a rare earth doped crystal where you have something called a mechanism which is called anti-Stokes cooling, where you basically shine in light with a frequency which is in the lowest possible transition frequencies that you have. And because of thermal excitation in the crystal, you can actually emit photons with more energy, therefore cooling your crystals. This technique has a lot of limitations nowadays that has to do with problems in material science, problems in the quantum optics of the process. And we have built a platform where we can easily change and easily try different materials on them. So currently we are trapping and we're doing Stokes thermometry already on many particles, and we're hoping that by the end of this year we can already do, here it should say single, not signal, single nanoparticle Stokes thermometry, and we can study thermal dynamics of traps, nanoparticles in the traps, and actually do anti-Stokes cooling. So with this I finish, so this is a picture of our of my students and me on one of the days that we get together to do pasta 1 or 2 years a year at home, and a very special member of the group, my dog Belko. Thank you very much.
Okay. Thank you very much. Now we go back to Brazil. We come back to Brazil for the last speaker. Who is Thiago. Okay, who is Thiago Alegre from Unicampi, and he's going to talk about optomechanics at the intersection of quantum systems. Please, Thiago.
Good morning, everyone. It's always a pleasure to be here, so thanks for the invitation. So I'll try to shed some light on some of the things that we're doing last couple of years in our group, and try to bring you to discussions about the idea of this optomechanics in a quantum system. So this is an introductory picture, but showing that the force, the optical force, is very old. But I want to call attention for two important things that happened in the 70s, which is one is trapped particles that we just learned, and the other one was Vladimir Baginski that also used the idea of optical force to measure mechanical vibrations on an interferometer and go to the extreme, where now he was one of the pioneers for using that to measure gravitational waves, and as we know. And the basic idea is this one. So you have an optical cavity, it shifts back and forth, and this shift back and forth actually give you a coupling into the optical frequency and the mechanics. And the key important here is that this squares, or it goes as the inverse of the length of the cavity. So microscopic objects can actually have a larger coupling. So that's why we went to the microscope world to do this sort of interaction here. And for those that are more familiar with Hamiltonian, the basic idea is that you have an optical and a mechanical system coupling together, and the interaction Hamiltonian depends on the number of photons and on the displacement. Okay, so that's the whole idea here. And as Christian just showed, you can actually do what he was just explaining now, that you can actually put a laser that is a frequency smaller than the cavity, and because of the scattering is more likely to happen in the cavity, you can actually cool down the system. So you have an optical version of the photon, therefore you are taking a phonon from your system, but you can do the opposite also. You can also shine a laser and actually create a photon resonance to the cavity, and therefore down converting your photon and creating a phonon. So in the classical domain, there are very nice works here. I just chose two. This one is one of the first one that show that actually you can parametric oscillate your microscopic object, and also you can cool your microscopic object. Okay? And the other one is this one here that was done by Gustavo, and where you can actually use the optical force to change the distance between two disks and tune the optical cavity. So one is the mechanics is optically actuated, and the other one, the photonics, is optically actuated, both in the not in the quantum regime. And the other two that I happen to work on both is that actually you can actually optically induce the ground state. So it's very tiny. So here's the cross where you measure the number of phonons and go down below one phonon. And I think the most important one actually is this one, which you measure the sideband symmetry like you do in atoms. And by showing that actually the scattering probability is larger for one side to the other, you are actually probing that you are in the quantum regime. And this actually is one of the standards nowadays to measure how close you are to the ground state. Okay? And in terms of a quantum network, you have like different layers of things that you can think about it. And we are more focused on some of the key aspects here. And one of them that Rodrigo just mentioned is the communication channel. So here's like the brute force way to do it. You connect two of the dilution fridge with a microwave, and we are looking on how to connect them with optics. But there are other things that you can do with optomechanics. So it's really like an intermediate state. So you can have like optics talking to optics using phonons. For example, this is a coherent transformation. So a frequency conversion, so to speak, from one frequency to the other using the mechanics. You can also like have like an optical mode that creates a phonon that travels back and forth, and you can use the phonon to interrogate your system, but again, you are measuring the optics. You can also talk to solid-state qubits. So you produce a perturbation in the mechanics system, which then, by stress or strain, changes the two-level system, and with that, you can actually interrogate your system. And you can also do what Rodrigo just showed you guys, which is by a phonon, you actually, by piezoelectricity, you talk to a microwave qubit. And that's also a transduction between a terahertz photon to a gigahertz photon, for example, using the mechanics. So again, like you always have like a mechanical mode and a piezoelectric device that actually talks to your qubit. And another thing that's very nice is that you can use the optomechanics as quantum memories. Since the difference in the frequency are so large, so this is like a terahertz and this is like gigahertz, you can have like a millisecond memory on gigahertz or tens of milliseconds memory in a megahertz regime. So that's also something that, in terms of the quantum, is very important to not only interconnect, but also use this as a memory. At Unicamp, we have like a zoo of things that we do in this area. And I'll try to just show, like, highlight 3 of them. This first one here is really like trying to understand a different regime where you are not only changing the frequency, but you are changing the losses of your system. So you are adding to the interaction Hamiltonian another term here. And this is due to the fact that you can actually have like 2 optical modes, and they have like a symmetric and anti-symmetric, and that actually is understood by the waveguide as a loss, an induced loss there. Okay, so it's a new regime. It has a very large. We show that we have a very large dissipative coupling, which could be used and actually could interfere. So you see, like there's a phase difference in between the Hamiltonians here. So actually, you can interfere constructively or destructively with the first one. The second one, this one actually was done in Delft. For Delft, Simon Groblacher was the one that led this project here, which was to create an entangled mode, 2 entangled mechanical modes. So like, for example, one device here and the other there. So we entangle the mechanical system here, and using an optical system, bell detection, you can actually teleport one state from one side to the other, in this case here. And Rodrigo was there, actually was working there with Simon. So again, like it is in the quantum world, it showed that you can actually teleport a mechanical state from one to the other. And the last one, but not least, is that in this case here, you still, the rate that you teleport, you're still limited by the fact that you hit your system with light that's scattered. So in this work here, we're trying to understand how this heat like dissipate and actually create an innovative design to have this in-plane heat dissipation. And that allowed us to have an increase in 10 times more photon per generation. And again, you see here like this asymmetry measurement that I was telling you in the beginning. So it's much, much larger than the first one's experiments, of course. But you see like scattering from the blue and red sides shows that you can actually have a very pure quantum system in the mechanical domain. And of course, this is also a very low residual heating. Of course, then not of this is only bright side. There's always like the dark side. So in this case here, for the quantum teleport, you still have residual heating. For this other one, you still don't have a full transduction. That's something that is still like in the game for everyone. And that's why I think that this is very important. And for the dissipative, we still need to do some experiments at low temperature and see if this phase difference between these two effects, if we can actually enhance the coupling into the low frequency domain. And just to mention, this work was led by Simon. Rodrigo was there working. Andrea was involved in this work and also like staying there for a year. So that's also to show that the connection that, unfortunately, I would like to have like Latin American people here. So we need to make like more connections here. But for example, André and Rodrigo went with a funding from FAPESP to stay a year abroad. And this other one, Gustavo was also involved in, and Simon provided samples for us. Okay. So with that, I end with the picture of our group and of course the founding agencies. And thank you for listening to this 5 minutes, a little bit more than 5. Thank you.
Thank you very much. So now that we ended with the talks, I think it's time to move to the roundtable. So I ask all the speakers to take a chair here. But no, I think I have to move back and forth for the questions. So, who is gonna start? Okay, apparently everybody's a bit shy, so I start. So let me start with Rodrigo. I anticipate that I'm not at all in the topic. I mean, I'm a theoretician, so I could ask very simple questions. So if I understand your, is it working? Okay, but now it's working.
Okay.
So if I understand your activity is mostly tailored toward making qubits talking to each other, right?
Yeah, like the final goal would be, yeah.
Okay, so let's say, as far as I understand, you are working assuming that the qubits that finally will win the race are the superconducting qubits, right? So I was wondering if your research is a little bit, let's say, agnostic about that and can be, let's say, converted in case other qubits will win the final competition or not?
It's a great question because first of all, like if you have like a great quantum processing unit, purely optical, most of it is it's not so useful anymore, right? Like to be honest, it is. But I think from what I understand from the field now, even though yes, there's a race and no clear winner, but superconducting circuits have been leading these sustainably over the last 10 years or so. And I'm pretty sure that it will be definitely an important platform for at least a couple of decades to see, you know, like, but it's not so agnostic, to be honest, you know, like.
I see.
First of all, yeah, just because of the range of frequencies that we are working, right? Like it's useful to think about these if you have a system working at the gigahertz range, for example. That's the case of my qubits. If you just have like optics, not so useful anymore, right? But I'm pretty sure that there's a lot to see. And even though if the transduction itself ends up not being so necessary, there is the control that we have of quantum states with superconducting circuits might be useful also for generating optical systems. Because if you look to the Wigner functions that you can create, for example, using superconducting qubits, is much more flexible and rich than what we have currently using purely optics. So even if it's just a source of like to help in the optical systems, I think it's something that will be useful for the future.
And what about, again, I'm talking about things that I don't fully understand. What about, as far as I understand, the third actor could be the possible ion qubits. What about that? Do you see applications or?
So yeah, the difficulty here is that you need like to have an intermediate that communicates well with both ends, right? Like, and there are some initiatives, especially like using magnons, for example. I know that's a big community growing in this field, but I think like as far as I know, like the field of transduction is more like focused on acoustics because of the way they behave independently. Electromechanics works very great, you know, like we can do great experience in the quantum regime using electromechanics, and so the same for optomechanics. So it's now the community is in this moment of trying to connect everything and make it work well as well, you know, like. But then, but yeah, there are like other more exotic initiatives. But I think from this field, for sure, like the electro-optomechanics is the most popular one, most popular approach.
And in Brazil, you are the only one focusing on, no, together
Yeah.
with the, yeah.
Thiago is also doing, yeah, I think in different lines, maybe one, two.
Yeah, maybe you want to.
Yeah. No, yeah, I think Rodrigo like explains very well like what's going on there. I think to have the control of the mechanics in this nano or micro world is important because you can interrogate like different systems. As I show, like there is also like, for example, even for NV centers, which you drive optically. So NV center is like a defect in the diamond. There's still like works done using the drive to be by phonos. And why is that? Because then you can actually directly drive with the optics. So you don't need like a microwave channel to go there. You actually drive directly and resonantly the transition with the system. So I think it's really like a platform and a rich platform that you can actually use it. And but of course, this is like one small. I think that you are fully correct. Nobody will win the race yet. So there are, for example, trapped ions that is being done on microscopic device that you can actually trap like tens of atoms that are very robust over the environment. Because I think one of the bad thing for this transduction using optomechanics is that you need to cool down. You need to go to the have a dilution fridge. This is actually not an advantage because if you think about like doing a quantum computation and you have like only 250 microwatts of power to cool a system, and if you want to scale up that to a football field full with this systems, it is not energetic, stable. So that's one thing that you can think about. But all the other tools that you make it, you can implement on other things. I think that's the good about it. So maybe like Christian.
Yeah, one of the, it's an interesting question because there's pros and cons of working with higher energy, right? So having transitions that you can address with laser light, of course, makes them being very far away from the temperatures that correspond to the thermal energies that we live in, which is nice, so you don't need to cool things so badly in order to decouple them from the environment. But then you have the problem of actually having lasers around and having to address lasers and stabilize lasers, which if you work with microwave or radio frequencies sources, it's all electronics. It's just turning on stuff that work. So there's always pros and cons between the two things, and actually this interfacing is always an interesting thing to look at. And in that respect, I think that one of the two different things that sideways we look in the lab. So I was telling, so we have this project which is more on ions, but then this other part which is more in solid state physics, and where actually one of the ideas is, okay, if you can actually, so we're looking into having like little cryostats, but that are optical cryostats. So one could actually think of doing experiments that require low temperatures, but not on a dilution cryostat, but on something that you can stick onto a particle that you can cool optically. That's also a nice way into getting low temperature physics without the overhead of a dilution cryostat, with another overhead probably. But it's another interesting pathway of doing low temperature and solid state physics, which is somehow always. So in a way, if you're looking for applications and technologies that can leave the lab, it seems better than having to do things in ultra high vacuum, as we have to do them for ions, which gives you these other advantages, which is you're very isolated. So I think I totally agree with the premise with respect to quantum technologies, both for sensors or for computing, if there ever is a reasonable information processing device, such as a computer around it. It's absolutely not clear what the technology will be. So it's good to explore different interconnectivities between technologies and the actual systems themselves.
Okay, let me also say that we have decent amount of people on the Zoom, so I encourage them to perhaps unmute and ask questions if they have, or write in the chat, but they can directly, let's say, unmute and talk. Other questions? Yeah, over there.
Yeah, I have a question to Christian. You showed us this nice ion trap. And the question is, what are your plans for it? What do you want to do with the ion trap? I mean, of course, as you mentioned, there are only two in South America. What are your plans for that?
So we have actually 3 ion traps in Buenos Aires. So it's the first ion trap that I showed, the one that had the ring shape. That trap, unfortunately, we've turned off a month or 2 ago. The idea with that ion trap, which was the first one we worked with, which was a very simple ion trap, which is actually meant for trapping very well one ion, not ion crystals. The idea was to do the first experiments where we were exploring different aspects of structured light-matter interaction, and then we were going to turn that ion trap into an optical clock, which is the new technologies, one of the emerging quantum technologies. But unfortunately, because of lack of funding, this project has been put on hold, and we've moved a lot of the electronics that we were using on that ion trap to the other one. On the second ion trap, which is the linear ion trap, which we have, which is the successor of the first one, the projects that we have, as I very briefly mentioned, are projects where we basically want to study quantum and so quantum thermal dynamics or thermodynamics at the low particle or almost quantum level, and also generation and control of non-classical states. So trying to explore having logical states in motional, encoded in motional states of ions. So that's a line of work with the ion trapping. And then, so why do we have, which one is the third one? The third one is the nanoparticle trap, which is also an ion trap, but it's not a single ion trap, but a nanoparticle which is charged, which in a way is a solid state ion.
You, okay.
Thank you all for the talks. I'd like to maybe divert a little bit from the science strictly, but try to connect the scenario that you guys put forth with Liliana's talk, which is you had this plot on the number of papers, co-authors in a paper. This is let's say a picture of the Brazilian community. A few weeks ago, we had a roundtable in this very building, and Antonio Zelachetti was mentioning this trace, let's call it, of the Brazilian community, that we've been doing this sort of single hero or few heroes experiments with not many people involved. And we contrasted that with Rafael Chaves, which you also mentioned, recent publications in partnership with Italian groups, where you would list sometimes 25, 30, 45 authors, right? And all the recent breakthroughs and big experiments have sort of surrendered to the fact that you need big collaborations to handle it, right? And I would like to perhaps bring Christian's perspective on the Argentinian side on how you see Argentina going in that direction. Your experiment, we know, is a tough experiment, right? It's a challenging one. And apart from yourself and your colleagues there, do you feel there's a network of people trying to, get these experiments bigger, more effort, more people in it? And then I would like Thiago and Rodrigo to mention, because in a way, we also like this. I mean, sometimes Thiago had a picture of a lot of people, but you look at the papers, these are mostly single group publications. So, and Rodrigo is just starting, right? So how do you see the new atmosphere at the University of São Paulo to sort of gather more people around a given goal?
So,
Maybe I can,
yes.
because I have to talk at one time. So this study, and particularly the collection of the data, led me to know very well what is the Brazilian scenario. And this is 2022, and the scenario of collaboration, it's a little different now, because now in Brazil, we have these 3 initiatives to create optical communication networks. And maybe Gustavo is going to talk about, I don't know, at the afternoon or right next, but we have this Rio Quântica, which is the junction of 5, I guess. It's one in Universidade Fluminense, then the CBPF, then the PUC, then the EMA, and there UFRJ. So all these people are using optic fiber connection that they have in the city of Rio de Janeiro, and then they are trying to create a channel of communication through the Guanabara Bay between CBPF and the Federal Fluminense, which is in Niterói. And this is a big initiative, and this is a project with a lot of groups collaborating together. And then it's another one in São Paulo, and another one in the northeast of the country, between 2 universities at that place. So I guess the scenario changed a lot. And we in Brazil, we have extremely strong groups in experimental physics, like Ivan Oliveira at the CBPF, which is involved in the Rio Quântica, and also they have NMR system, and also they are putting together some effort with Unicamp to produce the first chip, quantum chip, with transmons, hopefully. And in theoretical physics, we are very strong in quantum optics. So we have pioneers here. We have this privilege. And thermodynamical, quantum thermodynamics. Unfortunately, one of the leaders of the area, Gabriel Landi, left us. They went to Rochester. It was lost. But there are a lot of people really, really working hard in quantum thermodynamics. So it's nice to hear that maybe the quantum thermodynamics can be applied experimental here. So it was a good news for me. My expertise is I'm theoretician. I'm working in quantum dots and cavities. It's a little similar with I had to talk with Thiago Alegre. And not the best example of collaboration. I work with my group, only one group. It's not a good for me. But I think the Brazilian community is very strong, and it has a critical mass of people to do a breakout, I guess, I think. And we need funding. We need funding, and people who are more involved with these numbers and everything it's the following section, I think, is finance, is funding. So okay, thank you and forgive me.
So I will end up with a question, which I think it's interesting. I don't know if we will be able to answer it right now, but probably from your data, you have some insight on it. So one thing I mentioned, I think 2 times during my small talk, was we have a lot of informal collaborations, and actually, if you probably see the same kind of connections between Argentinians and Brazilian researchers, and I don't know how it's with the rest of Latin America also, probably there are not so many, actually, collaborations in written paper. So that end up in papers published together. And I do agree with Gustavo from the premise of your question, is big, interesting work comes from collaboration. So, and I would say, though, that the numbers that you showed, and like you say papers with 1 collaborator, 2 collaborators, I think those are very good numbers. So if you have a big chunk of papers with many collaborators, then it's very difficult that they're going to be the majority. Already, if you have a good proportion of them being of big collaborations, that's great. And then the question that I ask myself is, what is it that, so how is it, for example, this network helping that actually there are collaborations that end up in joint written papers in Brazil? What are the tools that are used so that actually ends up like that? Because we've been having joint conferences, we've been visiting each other, short visits, and helping each other around and exchanging information, but probably there's one next step that we have to think, which is the next step in order for that there's a really strong Latin American collaboration in quantum physics. Is it longer research stays? Is it interchange of students? What is it? I'm not sure what it is, but I think that an interesting question that we can ask ourselves is how can we, so not only continue a Brazilian network like the one that you have there, I think you showed results that are absolutely amazing, but also extend this to collaborations to other regions in Latin America.
I guess the traveling thing is very important. It's very important to, to contact, eye-to-eye contact. It's something that is important. Here in Brazil, we have this biannual event, which is Para Ti Quantum Information School and Workshop. And it's a beautiful place, so everyone want to be here at some time. And this, for me, is like a big pot when everybody talks together and and the students meet each other and it becomes friends. And friendship is something that evolves with time. And also in Brazil, we have this, I think it's, with all the problems and all the issues of funding, we have funding. We have these scholarships for CAPES and CNPq in the graduate schools. We have this ICT, the national institutes going out. It's a little slow because the funding goes like drops, it's dropping, and it's hard to plan for that. But I think that's the key. It's events, local events, when you bring people out from the outside together, and maybe increase these events. For instance, I think that the Initiative of Nanocarbon, the carbon people, they held an event annually, and it's like you have to go there. Everyone, every group has to send a representative, and their network is really amazing. The connection, they have a similar study, they copy us. So I have a similar study that never published it, but of course the connection is stronger than ours. So these annual meetings could be a good idea, because it's nothing like you have to present a paper and you have to expect to be accepted. No, it's like everybody in the ICT have to be, I don't know, in Sao Paulo for 3 days, and one of the students, and they raise the money and everybody goes there. Maybe it could be it's a good tool for yes, to have stronger communications, collaboration. And maybe a Latin American symposium, but we have Paraty and we have quantum optics in the area. So we talk together. And maybe it's good talk, I don't know, online, some online events here, something like that. It comes to my mind.
It's a question there from Paulo. I'm from Paulo.
So,
Much of a question, but a comment on there was a question related to networks in Argentina and so on, and the idea of collaborations. In order to collaborate, I think really fruitfully between different groups, you have to have some sort of critical mass in each group. Because, for example, I don't know, I admire Christian a lot. He was my student together with Miguel La Rotonda, but he has this wonderful lab, and he's the only senior researcher in the lab. So everything depends on him. Has no postdocs. The situation is like that and no money for postdocs, and hopefully we will get them now eventually a postdoc. So in order to collaborate, he has to be convinced of there is something within a time frame which is reasonable, that you can invest your times and energy and the students in order to move along that direction. And I have an anecdote. His PhD was in 2009 and 2010. 10 and 11, there were the 2 papers that were published, both published in Physical Review Letters. One was in the front cover. So they were 2 good papers on an implementation in an optical experiment, single photon experiments, of an algorithm, a quantum algorithm aimed at what is known as quantum process tomography. So you don't know what is a system, how a system is evolving, and you want to characterize the evolution of the system, what kind of experiment you have to do in order to get partial information, because if you want to get full information, it's exponentially expensive. And we had this theoretical algorithm a few years before that, and Christian's work at the beginning was to put that, to design the optical experiment in the optical table, and to come with a shopping list. What do we have to buy in order to do the experiment? And at that time, I talked to Steve and Paulao in Rio in a Paraty workshop. You were there, Christian. And we tried to convince them to do the experiment. And at that time, they were working on these wonderful experiments on the sudden death of entanglement. And Luis it was the first time that entanglement, sudden death was observed. I think, experimentally in the world, no? Luis, yes. So entanglement decays, but as opposed to what happens with energy that goes exponentially down, entanglement disappears at finite time. So this was observed, and it was impossible to convince. They were saying, okay, this is a very interesting experiment, so on, so on, so forth, but you have no people to do it. So we need to strengthen our groups, and to close, this is a horrible situation in Argentina at the moment. So we have a network I mean, there were some diagnostic of what we need to do in order to strengthen experimental groups, and there was a plan, and but now there is zero money, people are leaving. It's a disaster. We need more of a safety net because we are falling down. It's not a very optimistic point of view that I have in Argentina. Christian is sort of trying to resist, and the lab is trying to grow and to be attractive place, and it is a very attractive place, but it's not a good situation. So in this context, thinking of collaborations is very complicated. It's not easy.
I don't know if the debaters want to respond to Juan Pablo before.
Maybe I can make a comment. I think two things are important, as Pablo pointed out. One is you really to have students and a sort of like a critical mass. I think that's the way that you start collaborating. And in terms of, so in physics we have two models. One from the particle physics, which has like a gigantic collaboration, but they have a very well-structured way of communicating knowledge one to the other. Or you have to go to the lab. You have like to exchange students and personnel to be in the lab. And as far as I understood from INCT, and in small like comparison here in the state of São Paulo, the CEPIDs, they do have like lots of scholarships. So you attract people, you create the critical mass, and then you start to increase the interaction in between the groups. So I think that's the way that I see is that's the path to make like stronger and long-lasting collaboration. You first like attract students, have like enough students to, for example, to talk to other people, say like, oh, I have an experiment in mind. Okay, let's just do it right now, and then you can start collaborating. And I think that's a successful story from ENST.
Okay, well, first I would like to thank everybody for their presentations. I think it's very useful to see younger people showing the science that is going on, and that's building on a more longer-term tradition. I actually want to be a little more provocative in the following sense. First, you showed a lot of interaction with the outside world, with other regions, with North America, with Europe, with different groups. And in that sense, technologies that are being used here that are essentially at the state of the art of what other people are doing. Question. There's a lot of emphasis in the quantum community now on error correction. And this is a subject which we hardly see in our groups here. So I would like to listen to your view on that. The second, more provocative question or comment is in the opposite direction, actually. And that is, we've built over 25 years of very strong quantum science community in Latin America, not only in Brazil, but in Argentina, in Chile, Colombia, Mexico. So what can we do in terms of going forward towards technology in which we are really lacking and we're lagging behind that would be unique. Let's not just follow what other people are doing, but what can we do which are opportunities that are particular to the region, where it's not just that we will be up to date, but we can be world leaders. And I want to hear about your views on that. I have my own. I'll talk a little bit about my own in the following session.
Okay, maybe I can start this one because you mentioned quantum error correction, and I like the provocation because, well, so we are thinking about that actually because these are very important topics, particularly for scaling the superconducting circuits, right? And we know, like from literature and also from some work that I have done previously in the postdoc, that the superconducting circuits are very sensitive to environmental noise in general. It might be muons coming from cosmic rays, impinging on the chips, or even radiative things around the dilution fridge. And so we are starting to look at that actually in a connection with, inside USP actually, with the Department of Nuclear Physics there, because there's a student there that was very interesting to that. So we are starting, what I want to bring out is at least that we are starting to look at that and to see what kind of contributions we can have. Because I think for this particular case, since our concerns came more from the quantum information theory, there's a lot to learn from the particle physics field that we are completely ignorant about. And I think this type of connection also outside the quantum information community can bring to us a lot of knowledge, right? So, and this is a side project that we have there in the lab that I expect that will bring some good understanding at least of these, right? On what are the microscopic processes that lead to errors and how to correct them following up, right? And yeah, I don't know, well, this from my perspective, I don't know if in ions you want to mention something or optomechanics or...
Maybe I'll go for the second one, which is, it seems addressed to us here in Brazil. I think we still lack in Brazil a little bit of attractiveness to the young student to stay in Brazil. So half of my students are not in Brazil anymore. I'm not like the most like a senior guy here, but I already have like 3 generations, and half of them are out of Brazil. There are 2 in Canada, 1 in Netherlands, another one that is out now at Switzerland. So I think it's difficult to make to be world leading when you are exporting talenting and not bringing them back. That's one thing that it's a key thing to think about it. So we need to make the correct environment, and not only like a position or a specific position, the environment as a whole. And as Juan Pablo just mentioned, like now that he sees like that in Argentina is a very tough time. We had a very tough time a couple years ago here in Brazil also, which basically kicked out like lots of young talented students. We just heard about Gabriel Landi. He was one of the leaders in Brazil about quantum thermodynamics and left, and now he's like in Rochester. Maybe now he will come back because he's in Rochester and is a foreigner. But anyway, I think that's one key thing. In terms of like the technology, what you do here in Brazil, of course that I think you were one of the people that always like raise the flag about the agriculture. That's something that is very important in terms of economic for Brazil. So in terms of sensing, I think sensing is something that we could think about it. But if we only focus on a single place, we might miss. So we still need to look over also to quantum telecommunication, because that can be, and the networks that are being built in Rio de Janeiro, Recife, and also here in São Paulo, they're important also because of the sovereignty. You need to have a quantum communication system because you need to learn how to do it. You need to learn how to implement. You need to learn also if things that people are selling you are useless or not. So I think in that sense, and also quantum computation, you cannot lose sight of it. Because if that once became what is promised, we'll be lagging behind like decades. And it's very difficult to come up very quickly. See what's happening with AI nowadays. Okay, AI is now like a big thing, and actually the ones that are leading the race are the ones that actually invest money a long time ago on it. So, and now we are trying to catch up to be also world leading. And we do have like extremely very good and talented researchers in the quantum computation and engineering side of it. So, but again, I think it's a mixture. I think there's not a single answer for you, Paulo. I just don't think that we are always like only like. I think we are also leading some of the areas. It's not that we are like just bringing things from outside and copying here. I don't think that's what's happening nowadays. We are really like thinking forward. So, but maybe we could be more aggressive. Maybe that's your comment.
I'll make a small comment. I think I agree a lot with what you've just said, Thiago, but I think your set of questions is not only provocative, but also a little bit tricky, Paulo. Because in the first question, say like, hey, look what's happening outside. Are you paying attention to this? And then the other one is saying like, but why are you looking so much outside? So that's a difficult balance, yeah? It's a very, very difficult balance, saying like, okay, and I want to keep up, be like, not lose what's happening at the frontier of technology, which is definitely developed not mainly by us, but in the Northern Hemisphere by the principal countries, and also having an eye on, okay, how can this be useful for us? And I think there's definitely not a $1 million answer to the $1 million question, right? But keeping a strong research network is definitely a way of having a community ready to act whenever those opportunities appear. And having research grants and programs that actually open for questions that people might have answers is a way to go. I don't think we can answer the second question here, like saying like, this is what you should go for. But what we're doing here, I think it's the back end of then the front end, which is having actually grants for applications, having grants for other projects that might change our reality locally.
Little comment. And I think for the second question, Professor Paulo, I think there is something that we have to do, and it's to talk with our colleagues in engineering and in computation. And because they are interested, and they have this link with the private sector. So, and this is very important, I think. This is a first step. We are very strong together here in Brazil as physicists, thinking about quantum information and then a little of also quantum technologies. But now we need the engineers and we need the computer science people thinking with us. And in that, saying that, I think this first step is now we have these preliminary results of the new ICTs, the new institutes, and we have this one, which is the Computação Quântica Aplicada, Quantum Computation Applied. And this is a very interesting project because we have half of the people is physicists and half of the people is from computer science. So let us see what happened with that. I mean that in ICT. Hopefully I don't know when the final result is open, but this will be a very interesting experiment for putting these communities together. So I think this is a first step to trying to put something new in the world, I guess.
Okay, we are probably close to the end of the section, right? So maybe I
can ask one question.
Yeah, please.
So I think it's related to her comment, but in your labs, so you talk about the lack of people, but are your labs, the equipment come imported, or are they actually built in Brazil?
Well, most of it is imported. So yeah, important as well. But even like a small example, I was looking for an optical table to buy, and it's a relatively, like technologically, it's not such a complex device. And well, I couldn't find, to be honest, I found one company here in Brazil that produces it, but you see it's really like a few of them. Maybe you guys know more, so even like the simple equipment, we still have to import, right? Like, so it's a complicated, to mount a lab, I'm starting to learn now, but we need to deal much more with the importation than we need, I thought at the beginning, right? So, yeah.
I mean, it's even worse. Like, I can give you a much smaller example. There's a specific thread, screw, that we need to buy, and we have to import that because it's not produced in Brazil. We are not talking about rocket science here. So yes, I think that's what I'm saying, that about the environment. We need to create an environment that actually push people forward. And that will not be done only with physicists. We need to bring engineers together. And when you bring engineers together, they really like know how to raise the TRL, so to speak. So I think getting like all of these areas together is what makes like the next step. But yes, most of the equipment we import. Well, the things we fabricate in Brazil are also very good, but are minor. But for example, vacuum chamber we bought here in Brazil, which is something that you thought, okay, but that may, we can buy. There are companies, but there are small companies that are now attached to very high I would say like public calls. So this company in particular is attached to the synchrotron. So when synchrotron creates serials and serials start to make like the call, and this company grow, and now you can actually buy from them very easily vacuum parts, which is something that we know how to do it.
Okay, we have one last comment.
Just a very short comment. I cannot resist. I mean, I'm going to talk in the afternoon, but you're talking about imports. And you know that if you import an equipment for scientific use in Brazil, you don't pay taxes. However, if you buy an equipment which is produced in Brazil for scientific purposes, you have to pay taxes. Okay? And that's the case, for instance, of the nanoscope invented by Rodrigo at the Federal University of Minas Gerais, and the competition is very tough. Very tough. So Rodrigo, by the way, he's in Portugal now. Okay, so you know, small problems, small details, which must be solved here in Brazil. I have other comments, but since I'll be participating in the afternoon session, I reserve these comments for later. Thank you very much.
And can I just make one last comment? That's a story that Leonardo Menezes, which was a professor at UFPE, told me once, and I propagated. He got a PhD scholarship from Germany. So he went there, stayed like 4 years there, paid by the German government, came back to Brazil and set up his lab and bought 2 German lasers. And with that, he paid the whole scholarship back to Germany with only 2 lasers. So okay. That's another thing. If you think about as a country, that's a way to move forward.
Okay, I think it's time to wrap up the session. Let me just ask for the last time if people in the Zoom want to ask a question. Okay, apparently no. So let's thank all the speakers for this first roundtable. 30 minutes. Okay.